continue on here. Thank you so much for this water. That was a lifesaver. Okay, so I've got a population. You can't see what it is, but it just says population just has 100,000. Oh yeah, I did 10 to the 5. Okay, 100,000 numbers in there. Okay, so there's 100,000 people, and we can just look at maybe, I'm going to use bracket notation. And because population is just a list, there's no, you don't put a comma in there. Okay, you can just say, you know, give me the first 30, 1 through 30 entries in population. And we see these are different people. So this represents a person with an IQ of 91. This represents a person with an IQ of 103 or something like that. Okay. And I could ask, you know, what is the histogram of population? And it looks like that. I'm going to just increase the number of breaks so it looks a little bit prettier. Okay. All right, so our population looks like a normal distribution, which makes sense because I had the computer create these numbers based on the normal distribution. Okay? And we could ask for the actual mean of the population. Okay, and so the mean of all 100,000 people is exactly 99.96654. Is that okay with everyone? All right, so the mean is that, and we could ask for the standard deviation of our population. And the standard deviation is exactly 15.05710.701. Okay. So that is the standard deviation of our population and the mean of our population. And here I'm going to do random sampling here. Okay. So I use this function sample, and I'm going to sample population. And let's say I want to take a sample of 10 people from the population. Okay. So what this does is it's going to go into this list, not of 30, but of 100,000 people, and it's going to select 10 people at random from that out of 100,000. Okay. And those 10 people that selected are these. Okay. 109, 87, 101, 96, 99. So on and so forth, okay? And if I call it again, sample population, it's going to grab another set of 10 people. Okay, so every time you call sample, it goes into that list and it pulls out 10 people. Okay. What I want to do is, when I take the sample, I want to calculate the mean of the sample. Okay, so I'm going to store, okay, something, I'm going to just call it temp, and I'm going to store the output of sample. And you can't see it just because I stored it. Excuse me. I'm sorry, I don't know what's going on today. Okay, so these are the 10 people selected. And I could ask for the sample mean. What's that? All right. Okay, I'll take cough drops as well. I don't know what's going on. All right. My life is so hard. All right. I'm going to go home and tell this story. My wife will be like, you're late. Okay. And so our mean of these 10 numbers is 93.4. If I take another sample and calculate the mean there, the mean of another sample was 95. I do this again. And here I got a mean of 109. Okay? And so we can see that every time I'm taking a sample of 10, I'm going to get different numbers. Okay? So the average here was 109. Average was different like that. Okay. So let's do this a whole bunch of times. Let's say I do this 1,000 times. So I'm going to take 1,000 samples. Each time I take a sample, I'm going to take 10 numbers. And every time I take a sample, I'm going to calculate the mean. And we're going to keep track of all of those sample means. All right, so I'm going to build a loop here, okay? And so I'm going to just call, I'm going to create something called sample means. I'm just going to store 0 in there. And I'm going to build a loop. And I'm going to just say for I in 1 through 1,000, what I want R to do is basically take a sample from the population of 10 people and then calculate the mean of that sample. Oops. Okay, and so that's basically all I'm doing. I'm just saying take the sample and then calculate the mean of that sample. Okay, and what this does is it says store the mean of the sample into sample means, and I put a bracket I. Okay, and so in the beginning, I starts off at 1, and so it's going to store in the first position of sample means. And then it goes through it again and does it the second time. And it's going to do this 1,000 times, and it's going to store 1,000 different values of the mean of a sample. Okay, and I just say do that, and then it's done. Okay, I did it 1,000 times in a blink of an eye. It's like it was less than a second. Okay, and we can even see. All right, well, let's see what kind of values do we see in sample means. All right, instead of seeing all 1,000 of them, let's just look at the first 30 entries. Okay, and so we know these are the means of the samples because in the population we only have whole numbers, right? In the population, if I just look at the first 30 numbers, I only have whole numbers. And here I'm taking samples of 10 numbers, right? And so it makes sense that I have 1 decimal place. All right, so these are the different numbers, the different sample means. Okay, so what do you think the histogram of the sample means will look like? Any guesses here? So this is the population. So look at the population. We've got this normal distribution. Center at 100. Standard deviation of 15. All right, what do you think the histogram of the sample means is going to look like? Yeah, let's take a look. Okay, so yeah, let me just increase breaks here. It was like a higher number of breaks than what it defaults to. All right, so we're getting a weird. A little bit of weirdness, but yeah, we get something that still looks very normal. The mean is 100, but what do you notice about the range? The smallest values we see are down at 85, and the highest values we see are at 115, where the bulk is, I don't know, around 107 or something. Okay, and we can ask for, what is the mean of all of these sample means? And we're getting 100.1204. And I can ask for the standard deviation. Okay. So we see that the mean of all the sample means is very close to the original population mean, but the standard deviation is much smaller, at 4.8 versus 15, and we have 100 versus what was basically 100 as well before. Yes?
So the population standard deviation was set at 15?
Yeah, the population, so if I ask for the standard deviation of the population, we also have 15. Okay, we have 15. Something, or just something a little bit larger than 15. Okay.
So all the data is within, or never mind.
So this is the result of 1,000 different samples of size 10 each, taken from the population. Okay, I can repeat this. Just take this code here. And let's do 10,000 samples. And instead of samples of size 10, let's do samples of size, what? 30. Okay, what will happen if I run this? It takes a little bit longer to run because, oh, no, it's done. All right, let's take a look at the histogram here. Looks like that. Also very normal. Let's look at the mean and the standard deviation. Okay. And we see the standard deviation is even smaller here. Okay, when we increase the sample size, the standard deviation got even smaller. And that makes sense, right? If when we're selecting one individual at a time, we could get someone with a very high IQ. We could also get someone with a very low IQ. And that's just, we would just say, oh, well, that happens because of random chance. But if I'm selecting a group of 10 people, it's very unlikely for all 10 people to have very high IQs and thus give me an average or mean with a very high mean. Or if I'm selecting 30 people, it becomes even more unlikely for us to get a sample where all 30 randomly selected people have a very high average IQ. Okay, and that's what we're seeing here. Okay, when we're taking larger and larger samples, it becomes more and more unusual or more difficult for random sampling to produce a sample that is that has a mean that's more extreme or more unusual than what the bulk of the point, where the bulk of the points lie. So when for sampling distributions, what we see is that larger samples create smaller spread. Okay. This was an example where the population had a normal distribution. Okay. What do you think would happen if our population did not have a normal distribution and we took larger and larger samples?
It's not representative.
Okay, well let's see. Okay, so I'm going to create a new population. I'll call this Pop2, and population 2 is just going to be the numbers 0 through 9. Or you want 1 through 10? We'll do 0 through 9. Okay. So if I say histogram of Pop2, well, of course it's going to do that, but okay, there's like an optical illusion here, but something's going on. But anyway, basically, each digit 0, 1 through 1, 2, 3, 4, 5, 6, 7, 8, 9 has an equal chance of being selected. Okay, and so this time we're going to do random sampling. Okay, so I'm going to say sample from Pop2, and I want to take a random sample of size 10, but I have to turn replace it equals true. Okay, and so what that says is, because there's only 10 numbers in the population, so take a number, but then put it back, mix it up before you take another number. Okay, so this is a population where the digits 0 through 9 are equally likely, and so I get all of these numbers. Okay, this is what it spits out. And I could say, oh, okay, well, do this again, and we're going to do the same thing. And I say, I want the, and we want the mean of this. Okay, and so the mean of some 10 randomly selected numbers was 4.4. So I can do this over and over and over again. Okay. So here I'm going to do the same thing, but instead of population, I'm going to use population 2. Take samples of size 10, and I have to say replace equals true. We're going to run this. right, let's take a look here. Data. Wrong window. Histogram of sample means. All right, what do you think our histogram looks like? I've taken samples of size 10 from a population where the digits 0 through 9 are equally likely. Okay, and so we're going to see numbers in here anywhere from 0 to 9, because we're taking an average of 10 randomly selected digits. What do you think our histogram will look like? Same? Same as population 2, or? Well, let's see. That's what it looks like, okay? It looks like a normal distribution. So we're taking the digits 0 through 9, and what we're seeing is that when we average a random selection of 10 digits, the most common sample means that we're getting are right around 4.5, between 4 and 5, okay? And so, you know, if we ask for what's the mean of population 2, we get 4.5, and I can ask for the standard deviation of population 2, and I get that. I can ask for the mean of the sample means, and I get something very close to 4.5. And the standard deviation, though, is much smaller. And the shape of our sampling distribution doesn't look anything like the population. Okay, the population had this uniform distribution where each digit was equally likely. And what we're seeing here is that we're getting something that looks very normal. In my last quarter, I bored the students to death, I think, by demonstrating different populations, okay? I had, but basically, and this is a very interesting result, it's called the central limit theorem, and it's that no matter what your population looks like, whether it's uniform, normal distribution, bimodal, skewed, whatever it is, if you take samples over and over and over again, as long as your sample is what we say, quote, large enough, the distribution, your sampling distribution, when you look at the different sample means, your Y bars, your sampling distribution ends up looking like the normal distribution. That's the that's basically what the central limit theorem says, and it's actually quite a remarkable remarkable result. Okay, and I could demonstrate different shaped populations here, but will you guys just trust me when I say that happens? Okay, all right. So I think yeah, last quarter the students were like, "Oh my gosh, we get it." So I won't do that this time. What about a very left skewed? I'm sorry, what's your question?
Yeah, even a really skewed population.
So yeah, if you have a, so there's the caveat is, or I guess the warning, yeah, is that when we're talking about this central limit theorem and saying that the sampling distribution ends up looking like the normal distribution, there's kind of this a cheat where we say, well, as long as the sample is large enough, okay? And so it holds true. It holds true even for very skewed distributions, except your sample has to be very large. Okay, your sample is going to have to be very large if it's very skewed. Okay. So let me just recenter this. So the sampling distribution. Okay, so the sampling distribution will look like the normal distribution. Okay. If the population has mean mu and standard deviation sigma, then the sampling distribution will have mean equal to mu, standard deviation equal to sigma over the square root of n, where n is your sample size. Because again, what we're doing is we're repeatedly taking samples of size n over and over from the population. Okay. The sampling distribution will look like the normal distribution star as long as n is large enough. So no matter what the population looks like, it's going to end up looking like the normal distribution. That's the central limit there. Okay. I'll write that on the board as well. So it's not normal, or has a weird shape. The sampling distribution will look normal. Okay, that's known as the central limit theorem. This is a very loose definition of the central limit theorem. The real definition is a lot more formal than this. Okay. But again, as long as n is large enough. Okay, so what does large enough mean? Okay. Well, if the population is normal, any sample is large enough. Okay. Most populations, for most populations, n greater than or equal to 30 is large enough. But for very skewed distributions, you will need an even larger n. And there's no upper bound to what size you will need. It's just that when you take a very large sample, maybe it ends up looking like the normal distribution with mean, mu, and standard deviation sigma over the square root of it. But if it's very skewed, you might need a very large sample. And if it's very skewed, it might be easier to deal with logarithms of the numbers instead. You have to do a log transform, especially for things like income where you have people literally making over 1,000 times as much as another person within the population, where values are magnitudes, orders of magnitude greater, and not just, 10 times more. You get some people literally making 1,000 times more than someone else. Okay, so that is sampling distributions. Okay, so let's just check your understanding here. Okay, and so the key here is that you got mean mu, standard deviation sigma over the square root of n. So let me give you an exercise here. So I will say IQ scores come from a normal distribution with mean 100 and standard deviation 15. Okay, so that's shorthand to say mean 100, standard deviation 15. I'm going to say if you select a person at random, what is the probability this person's IQ is over 110? Okay. And then question 2 will be, if you select 9 people at random, what is the probability that their average IQ is over 110? Okay, go ahead and try that out. You'll need your normal model table. Okay, so need another minute. Are you good? So this is the population here.
How large is the
Hmm?
How large is the N?
How large is the n? Let's it's revealed in this question here.
Oh.
Okay. Well, I know some of you guys are still working, but let's go over this. So here, this first question is just a normal model problem. We've got, IQs coming from normal distribution with mean 100, standard deviation 15, and I'm asking, what is the probability that someone has a IQ over 110? Okay, so I've got a normal model centered at 100. I'm drawing a cutoff line at 110, and I want to know how much is shaded over here. Okay, so I do z is equal to 110 minus the mean of 100 over 15. I get a z of 0.67. And I could look up 0.67 in the table, or z equals, and subtract that area from 1. If I do that, 0.67 gives me 0.7486. So the area to the left is equal to 0.7486. I can subtract that from 1. And I get 0.2514. Or conversely, I could have looked up the area to the left of negative 0.67, and I would have gotten 0.2514. Okay, so there's about a 25% chance that a randomly selected person has an IQ over 110. Okay, this problem, this is now dealing with a sampling distribution. It says we're selecting 9 people at random, so that's a random sample of 9 people. And we're asking, what is the probability that their average IQ is over 110? Okay, so here we're saying the distribution of y bar comes from a normal distribution where the mean is the same as the population 100, but the standard deviation is now sigma over the square root of n. So 15 over the square root of 9, where the standard deviation is now 5. Can we see the difference here from the way this problem is written? Okay, so this is now dealing not with individuals, but now groups of 9 people, and we're looking at the average of those 9 people. So we're not asking what's the probability that any one person in that group of 9. It's about what is the probability that all 9, that their average of the 9 people have an IQ over 110. Okay. And so here, you can now picture a skinnier distribution, 100, and I'm going out to 110. Z is 110 minus 100, divided by the standard deviation of 5. I now get a z-score of 2. Again, I can look up the area to the left of 2, or the area to the left of negative 2, and I get the area over here. Area to the right of 2 is equal to 0.0228. Yes?
Sorry, so if the population was really shaped,
Yeah.
you couldn't answer the first question, but you could answer the second question.
Okay, if the population was really weirdly shaped, perhaps, yeah, you would not be able to answer the first question. And the second question, it might be a little risky to answer it because your sample is only size 9. Okay? If your population is symmetric, probably size 9 is probably going to be okay. But if it's weird shaped, and I don't know what you mean by weird shaped.
Like really skewed.
Okay, if it's really skewed, then a sample of size 9 is not going to be enough to say it's normal. Okay, but here, I said the population is normally distributed, and so that means samples of size 9 will be big enough for us to use the central limit theorem. Okay, where we're saying y bar has a normal distribution. Okay. In other situations, we've only learned how to answer these types of questions when the population is normal. Okay, so in other types of situations where the population is not normal, you probably couldn't answer this type of question. What's the probability that some number is going to be bigger than some number? Okay, we don't know, all right, unless the population has a defined distribution. Over here, we can start to answer these types of questions because of the central limit theorem. All right. So even if the population wasn't normal, so I could, we could try another example. So I could say, and I have no idea, but let's say, so human weight is not normally distributed, okay? Human weight is right skewed. Okay. Maybe the mean, and I'm making this number up because I really don't know what it is, but I'm going to say the mean is 165 pounds. Okay, and again, I'm making this number up, and I'm going to say the standard deviation is 40 pounds. Again, I'm making this number up as well. So don't hold me to these numbers. Okay, so we don't know what the population looks like,